Everyone, this is Dr. M. Sohail Pervez from Anjuman College of Engineering and Technology, Nagpur. And today we are going to discuss the subject of machine design, in which we have outlined the today's lecture's topic, that is Introduction to Machine Design, Types of Machine Design Processes, Design for Static and Dynamic Loading, Fatigue and Endurance. This is one of the most important aspects in the design. ACET diagram, and then theories of failure. So, as far as machine design is concerned, first of all, we must know the basic meaning of a machine. As we all might have gone through the basic definition, that is the creation of new and better machines and improving the existing one, that is called a machine design. But what is machine? A machine which converts one form of energy into another form, or the mechanical energy in one form to another form. Now, when we say machine design, the subject deals with the design of machine parts using creative thinking, scientific principles, and technical information, so that whatever we have prescribed as a desired or the task to that particular machine should be accomplished by that machine with maximum efficiency and economy. Now, when we say machine design, again, I'm repeating the word creation of new and better machines. Now, when we say creation of new, it means new. Bicycle, when it was firstly designed, it was a creation. Wheel, when it was firstly designed, it was a creation. Now, when we say and better machines, it means already existing one, we have to improve the already existing machines. And since we are doing it, so every while now, we are classifying the type of machine design also. Now, why do we require the knowledge of machine design? Because since we are mechanical engineers, we are designers. Why do we need to go through all these steps, all this information? The very basic aspect is to select proper material and best suited shapes for the components which we want to design for the machines. Next one, to calculate dimensions based on the loads on machines and strength of material. And third, again very important, to specify manufacturing process for the design component. Now, when we say manufacturing process for the design component, so we have to have the specifications written on our design sheets, on our design tables, on our design files now. Since we are in the era of computer-aided design and computer-aided manufacturing, we have to have those soft files with us, where every single detail, right from the dimensions to the tolerances to the clearances to the manufacturing process, as well as the different views of an object. Hence, the machine design process can be broadly classified, because when we say creation, it means absolutely new design. But what about the improvement? What about the existing design? Because existing design which we have developed it, say 50 years ago, the same should not be continued as a design till now. So it is highly recommended that we continuously go on improving the existing designs. So these are the three basic types of design. That is adaptive design. It is concerned with the adaptation of existing idea and making minor alterations or modifications in the existing design for overall improvement. Now see, when we say adaptation, it means already it exists there, and we have to have minor alterations so that some efficiency, some performance may be improved due to or owing to that particular small alterations. IC engine. See from where we have started: 2-stroke IC engine, 4-stroke IC engine, and now MPFI, multi-point fuel injection system. So all these are nothing but the adaptation of the basic design of that engine, and we are going say going on adding the features. That is nothing but the adaptation. So adapting, and now a very minor changes. If the changes are say at large scale, then it is development design. But that counts for the another type. Turret lathes, press work, or the presses. All these are very robust. All these are very highly precise designs. But still, some alterations can be made for increasing the efficiency or the performance of that machine. The next target is development design. Now, when we say development design, it is concerned with the modification in the existing design into a new idea by adapting new material. This is very important. In adaptation, we go for minor alterations. If you may consider this example, as far as our Bajaj scooter was concerned, we were having only main stand there. But as the time passes and people came to know the importance of that particular side stand, because most of the customers have complained about the back pain due to that small pulling mechanism. So what we have done, we have added a small side stand there. So it was adaptation. But when we say new idea and by adopting new material or different method of manufacturing, now this is called development design. This is where the department lies with research and development. Here the research and development will come into existence. Now, to quote the examples, I'm giving you the very basic and simple example, displays in bike. Since we are much acquainted with the development in bikes. So previously, you take the example of Hero Honda. So Hero Honda display, it was analog display. The type of display was analog. Now over the period, we have developed through our continuous research and improvement, we have developed now the digital displays, wherein we can directly show that our bike is running at a speed of say 65.7 kilometer per hour, whereas in analog it was not very possible. Automobile body shape, automobile parts, because every new model will have a different body geometry, will have different curvatures, will have a more improved the original machines to the reformed or the improved development designs. And the last one is the creative or new design. Now, when I say creative or new design, it is also known as functional design because it is concerned with the creation of new design, which requires lots of research. Now, when we say lots of research, means we have to start with the scratch. The basic idea will come into our mind, and that idea is to be put up on a piece of paper through drawings. That's why engineering drawing is considered to be the language of engineer. Creative thinking, you have to think creatively, because unless and until a demand or a requirement doesn't comes to you, it is difficult that you think in that particular direction. And the technical ability, wherein you have to apply the technical knowledge which we are learning through different subjects in our syllabus to assure that the product will function the product will function properly for the specified period. Now, this is very important when we say for the specified period. Now, specified period, this specified period is nothing but which a designer is specifying for that particular product. This we will discuss later on regarding the specified period. The other way of classifying types of design is based on the types of methods used as. Now, when I say the different types used, it means rational design, wherein some proportions have been designed by the designers. The next one is empirical design, wherein some empirical relations have been put up, as we all know, the design of knuckle joint and the quarter joint. The next is industrial design, based on the necessity at the industrial sites and shop floors. We go for the industrial design. System design, the system of generated design, wherein two different systems are being assembled together. One is converting one form of energy or fuel into another form, and then that particular rotational energy is being converted into electricity by some other setup. So system design. Element design. Element is nothing but the singular part of a system, wherein that element design is equally important. The next is optimum design, because we all are aware that optimum design is utmost requirement of the industry as well as customer. So optimum design. But these are the different ways of classification. And then now computer aided design, we are all aware of this particular computer aided design. Now, since we are studying this machine design subject, so we have to have different considerations known to us, because whenever we want to design a certain product or a particular component or a mechanism or a system or a machine, you have to consider number of points. Because simply going, okay, just I want to design a bike or a bicycle for this purpose. Now, we have to have general design considerations there. These design considerations are nothing but the type of load and stresses, motion of machine parts, selection of material. So this is very important aspect. Now, when I say motion, when I say the motion of machine part and a selection of material, this is very important. These are two different elements. Motion of the machine parts. When we say type of load and stresses, how many different types of load do we know? So we will come on to this particular topic, that is load. What is loading and different types of loading, and what do you mean by stresses? Because in strength of material, you might have gone through this topic. It is an external agency. A load is an external agency which changes or tends to change the state of rest or uniform motion of a body. But this definition was hold good for the subject of engineering mechanics. Now, when it comes to machine design, it will create some stress, it will create some displacement, and thereby generating some stresses. The next is motion of that part, whether the part will be moving in linear direction, in rotation, in oscillation. Now, when we say selection of material, the broad classification of material is on the basis of either it is ductile or brittle. Then there are a number of sub-classifications depending upon the chemical and physical properties. Form and size of the part. What would be the form and size of the part that is to be designed? So we have to consider form and size also. Now, say for example, you are expected to design a bike wherein you are designing the side mirror. In that case, what would be the form and what would be the size of that particular side mirror, that you have to consider. Because simply you have to see into the side mirror is not a singular or the required or desired element. You have to have the form also, frictional resistance and lubrication. You might have gone through this particular topic, or you have seen this in DME also, design of machine elements. But still, when we say frictional resistance and lubrication, a machine designer or a design engineer should know where the components will come in contact with each other and how much friction will be developed and how to minimize that friction through lubrication by providing number of ports, number of facilities for lubrication. Convenient and economical features. These general design considerations, that convenient and design economical features, these are nothing but the features which we do provide for the components, for the design. Let us take the example of your bike, wherein accelerator is on right side generally or mostly, and the clutch is on the left hand side. Why do we keep this? Because on the right hand side, if you want to accelerate, then you have to control the clutch also. It is manually controlled. Nowadays there are automatic controls also. So you have to provide. Suppose see if we provide accelerator as well as clutch lever on the same side, on the same hand, then it would be difficult for us and it would not be the convenient part. Then again, use of standard parts. Say we have designed a bolt for a certain application and the diameter is coming out to be 9.2 mm. Now when we say 9.2 mm, the dimension is to be manufactured or fabricated in the workshop with the 9.2 mm diameter. But if you go in market, you will get a bolt of 9.5 mm diameter also and 10 mm also. And it would cost cheaper as compared to the fabricated or the product produced part in your workshop. So we should try to use standard parts. And again, the safety of operation is the utmost requirement. That's why we go for glasses, shields, face masks, and then aprons, boots, and likewise. The next important consideration is number of machines to be manufactured and cost of construction of the facilities or the workshop facilities. So thus we say, when we want to go for designing a particular machine, the general consideration we should be kept in mind are these, which are briefly explained here. Now, since today we are emphasizing on the design for static and dynamic loading, so that's why we must ensure to understand this fact. And I hope you are trying to listen this lecture carefully, since most of the topics are nothing but the revisions, but these topics will be used in the machine design processes now onwards. As we all know, when we say design for static and dynamic loading, first of all we should get again say a revision of what do you mean by loading. It may be defined as the external agency that cause stresses, deformations, or acceleration in the body or structures when applied. So basically, load is an external agency. It is not developing within the body. It has been applied on the body. And the loading may be due to, sir, the very basic and the most considerable reason is the energy transmitted by machine element. It will apply some load, dead weight of the machine, dead weight of the components, inertial forces, inertia by virtue of their position as well as the mass they are having, thermal loading due to temperature, frictional forces. Obviously, when we say frictional forces, these are nothing but the disastrous motion wherein the surfaces gets rubbed off or weared off. So we have to think how the loading will be done or how the load will act on our machine or component or element by virtue of all these things. The next is types of load. Now please understand this basic classification. See, there are different classifications, but as far as design is concerned, we have to go through all these four types. Number one is static, number two is dynamic, number three is impact, and number four is fatigue. Now, when we say static load, it means a load which does not change its magnitude, direction, or point of application with respect to time. Now, here the time is very important. Time is very important. It should not change with time, either magnitude or direction or point of application. So, for the sake of simple explanation, I have quoted an example: tension in truss member. So, in a structural member or the truss member, the tension that does not change its magnitude nor direction or the point of application. The next one is dynamic. That is the dynamic load. Changes its magnitude, direction, and point of application. Now you may consider this example wherein we can say that a shaft is subjected to a point load, and the shaft is rotating Now here even though magnitude is not changing, but the direction of the load is changing. The fibers on the fibers on the top will experience compression, and the fibers at the bottom will experience tension. Whereas if I rotate this half the rotation, in that case, the fibers on the upper side, which were previously in tension, will now be subjected to compression, and the compression will be subjected to tension. Similar is the case wherein all the three, that is magnitude, direction, and point of application changes. I have quoted an example of IC engine valve. So IC engine valve, that is the most suitable example as far as beginners are concerned, because we know that that particular IC engine valve spring, it is subjected to, depending upon the throttling, depending upon our acceleration, it is subjected to the amount or the magnitude, sir, in this direction. The magnitude goes on changing, fluctuating, rather, to be more precise. The direction changes. Tension, compression, and the point of application. Yes, if it is the case of your shock absorber, then you can very well justify this element, that point of application changes. So the dynamic loading. Third is impact. I don't think this is very much difficult for all of us. Suddenly applied with some velocity, the blow of hammer. And the last one is fatigue. When we say fatigue, it simply means due to repetitive work, due to monotonous work, a person starts feeling low. Even though he has not worked over his or her expected duration of time. The same is the case with the material, wherein we apply alternating or repeated loading, that is called cyclic loading. In that case, since the direction is changing and it is repeated, monotonous work is there. Now just take the example of your spring only in your bike, and you please drive through, not on the cement road or on the tar road, you drive on the the old roads. Now, in that case, you will experience the nature of repetitive loading on that particular spring. Again, the IC engine of your, or valve spring of your IC engine. So in this case, in fatigue, the object or the element may fail well below its desirable stress or strength. It will fail below its desirable or expected range. So rotating shaft subjected to bending load. This is again the example which I have quoted for fatigue loading. This we will, I'll again deliberate this with the examples if we move further on. Static load, the load which does not change in magnitude or direction and gradually increases to a steady value. Example, dead weight of machine element. As far as dead weight of machine element is concerned, where no such changes would be present. Now, why do we require to study the type of loading? Because since if you are observing design for static and dynamic loading, since this is our heading, subtopic heading for this today's lecture, why do we expect to study all these things? Okay, which type of load is acting on our component which is required to be designed? Sorry. So determination of appropriate loads acting on a machine member is a critical and challenging task. Why? All the stress and deflection analysis is useless and the component cannot function satisfactorily if the operating loads are not calculated or predicted correctly. Now, it is as a mechanical engineer, as a design engineer, it is our duty to exactly calculate the type of load acting on our component. Nature of loading, whether it is tensile, compressive, whether it is shear, whether it is bending. But as far as determination is concerned, sometimes it becomes very difficult. Now, say for example, our bike, or a bicycle is standing on a side stand, a temporary stand. In that case, how would you calculate the load acting on that particular inclined stand or side stand? So determination of load on our component is again a very difficult and important task. That's why we have classified our studies based on static and dynamic loading. Now I have put it an example of shaft running at known speed and transmitting known torque. We can calculate based on this torque and speed, we can calculate the operating load acting on that particular shaft. Now, design for simple stress, that is static load. And I think we should go say thoroughly over this particular issue, because as far as the topic is concerned, I am quite sure you have studied this in strength of material subject, but still I am revising this for the sake of building up that particular concept, so that we have to design the components in the next lectures to come now. So mechanical component is subjected to external load. A resisting force is set up within the component. This resisting force per unit of area of the component is called stress. What is stress? We generally discuss with our friends or family, I'm in tension, I'm having stress. What is that stress? That stress is nothing but the reaction of different circumstances on a human body, emotionally, psychologically, physically. Similar is the case with the stress on the components. Now, when we say component is stressed, it means it has to be subjected to some external load. Now, the maximum stress developed in a member should not have some working capacity under the working load, working condition, and say variable parameters. So in that case, how we should design? So all of you please mark this particular line and keep this thing in mind, that we have to have this condition, the last condition satisfied, known as design equation. The induced stress in or component to be designed should never be more than the allowable stress. You please keep this word allowable stress. Here it is not shown. In the subsequent pages you will come to know about this. So allowable stresses. So induced stress, whatever load is applied at present on that particular component, and due to that load some stress would be developed or resisted or generated, that stress should not increase the allowable strength of that particular material. That's why some limiting values of dimension desired can be calculated by equating, sir, this is very important, induced stress, at least it should be minimum or equal to the allowable stress. So this is, I am repeating over and over, this equation is very important, that is known as design equation. Now see, these are the different types of stresses going to the different types of loading, and I think this is quite clear from the diagram itself. So we can simply go on looking over to this particular PowerPoint slides. So direct tensile, so this is direct tensile or compressive and compressive strength. So tensile, if it is tensile sigma T is equals to P by A, again it should be less than allowable stress. In bracket, if we are reading this notation, it is allowable stress. And how allowable stress is calculated, we will see. Compressive strength sigma C, again it should be less than allowable compressive strength of the material. Shear, and I'm quite sure you are much aware of the nature of stresses. When we say tensile, it is pulling. When we say compressive, it is pushing. When we say direct shear, it is, please concentrate, it is in this fashion. The load, the forces, the loads are applied tangentially. Whereas in direct tensile and compressive, the loads are applied axially. So these are axial loads. Direct tensile and compressive stresses or loads are axial load, whereas direct shear is nothing but tangential. There should be some difference between the lines of action of these forces. Let it be tensile or let it be compressive. So direct shear. The next one is bending. The resistance to deflection generally used in bending. The bending is used in beams, the horizontal structural members. And if it is a column, it is known as buckling. Bending is used in beams. Buckling, the word buckling is used in columns. So this is the equation wherein sigma B is equals to M into Y by I, where M is maximum bending moment, Y is the distance, I is moment of inertia. Sigma B bending strength. Torsional shear stress. Torsion. When two equal and opposite couples, when I say two equal and opposite couples, so this type of twisting is applied over the ends of a shaft, it would create or produce a torsional shear effect. It may fail in shear because two equal and opposite couples are being applied at the ends. So the torsional shear. The next one is bearing or crushing stress. Because of this we have all studied in SOM. So I am going a little faster over this issue because this is simply the revision of these stresses, and we'll be using these stresses over the period of time for designing the components. Thermal stresses. See, bearing stress, we have taken the example. We have taken the example for this, a journal. Journal means shaft, a rotating journal in the bearing, and whereas we say that the the pressure distribution chart or the pressure distribution diagram of this shaft over the bearing surface is shown. So this is called bearing stress. Whereas by considering an example of two plates riveted by a single rivet. So when tangential force is applied in two different directions, this rivet may fail along this joint of two plates or along one single plane. It is known as single shear. If this rivet fails along two different planes, then it is called double shear. In single shear, we have got two pieces of a rod or a shank of that particular rivet. Whereas if we are getting three pieces, we may say it is a double shear. So this is basic definition of bearing or crushing stress is localized compressive stress. Localized compressive stress acting on certain projected area. So load upon projected area. So this is nothing but the bearing or crushing stress. The last one, as far as classification is concerned, thermal stress. As we all know, material expands on heating and regains its original shape after some time if we cool it down to the original temperature. But you please consider this example that if this rod, I think you are concentrating. So if this rod is fixed at one end and the temperature of the other end which is free, if I'm increasing temperature of the other end, in that case this rod will definitely expand in one direction. On the other side it won't have enough space to expand. The third case is if I'm heating this rod by fixing this rod fixed from both the or at both the ends, and if I increase the temperature of this rod, in that case due to this restriction the temperature will definitely try to put this rod under tension. So it will try to expand and these supports will try to compress it. Due to this particular mismatch, stress will be developed known as thermal stress. Most of the time we come across the design for thermal stress also, and we will be doing that. Now, after learning static loading, I am introducing again a very important factor known as factor of safety. The very first I think discussion should be there, why we require factor of safety. This is the basic I think requirement of today's lecture. Why do we consider factor of safety? So first we'll go for this slide. For design purpose, an allowable stress is used in place of the critical stress to take into account the following uncertainties. Now these uncertainties are very natural and very common. We have to consider these uncertainties in the machine designing process, and hence we have to consider factor of safety. Uncertainties in loading. Sometimes the load is gradual, sometimes it may be impact, sometimes it may be cyclic. In homogeneity of the material, we generally consider that this rod is made from some SAE 1020 steel, but whether that 1020 steel is really homogeneous over all the shafts of surfaces, over the entire structure of that particular shaft, doubtful. Various material behaviors such as corrosion, plastic flow creep may be there. Residual stresses, this is again a very serious issue. That's why we generally go for, what do we go for? To relieve these residual stresses, we go for heat treatment of that particular part, generally gears, bolts, shafts. We go for heat treatment, carburizing, case hardening, n number of processes are there. Again, the load is, if it is the load is fluctuating, then fatigue nature, repetitive loading is there, and the most important aspect is safety and reliability. So why do we consider, for design purpose, why do we consider factor of safety? So again, I am repeating, if the induced stress is less than or equal to limiting material strength, then the design component may be considered to be safe. An indication about the size of the component is obtained. Now, again, we are going back. Now, this is the definition for factor of safety. The ratio of maximum permissible stress of a material. Yes, maximum permissible stress of a material known as the limiting stress to allowable load or stress known as factor of safety. Now, when I say limiting, it does depends on the type of material. As far as broad classification of the materials in engineering design is concerned, we go for ductile materials and we go for brittle materials. So, for ductile materials, we use yield point stress as the limiting stress. So, yield stress upon allowable stress, and for brittle material, ultimate stress upon allowable stress. So, this is the basic relation we may write for the allowable stress as SY, generally SYT upon factor of safety for ductile material, and for brittle material, the allowable stress, this is the allowable stress, this is the allowable stress. So allowable stress SUT upon factor of safety for brittle material. Here we do consider yield strength in tension, and this is ultimate strength in tension. And I'm hopeful that these two terms are very much clear to all of us, because which we have studied in some, the stress strain curve, the basic stress strain curve, which we plot for either ductile or brittle material by conducting a test on universal testing machine and plotting the graph. We get different characteristics points, and those characteristic points are the decisive factor in deciding the factor of safety, and where the material will be considered to be failed. Again, deliberations will be there on the failure criteria also. So this is all about the factor of safety, because we are entering into the next topic, that is design for dynamic loading. Now, when I say design for dynamic loading, where both magnitude and direction, magnitude alone or direction alone or both may change with respect to time, known as dynamic loading. Cyclic loading is one of the name given for repetitive nature of loading. We'll be having with example, and I'll be explaining this basic factor. Although up till now it may look that the theory is, I think, more predominant in this lecture, because we have to clear all the basics. From next lecture onwards, we have to design, actually we have to do the calculations. So in that case, first we'll clear all these factors. Now let us consider this shaft. A shaft is rotating with some speed n, subjected to some torque T, and applied with some vertical load. Since the position of the shaft or over the length, the shaft is supported at the ends, then this shaft will bend also. Now, as far as static loading was concerned, static loading, we can calculate it by simply putting the value of load, that is stress is equals to force per unit or load per unit area. But in dynamic loading, we have to calculate, because in this case the load may be not always in single plane. It may be in double plane or in triple plane or three planes, three perpendicular planes. So now in this case, if the shaft is twisting or rotating with some torque, and if it is simultaneously bending also, then it would be very difficult for us to directly calculate using the principles of static loading. So the next one, A typical stress cycle is shown in this figure, where the maximum, minimum, mean, and variable stresses are indicated. I must again remind you all that in the static loading, we never have heard these maximum, minimum, mean, and variable. It was simply stress depending upon the nature of force applied, that is tensile, so tensile stress, compressive, compressive stress, shear stress, bending stress. Now here we will come across these four terms all the way. So please try to understand it, where the maximum and minimum, I don't think maximum minimum requires some explanation, but still the maximum stress developed on the component during a cycle, so maximum and minimum. What do I mean? Mean is nothing but the average of maximum and minimum. Yes, sir. Mean value and the variable. Sigma max minus sigma mean by 2. The graph is self-explanatory. Whereas this is mean line, mean stress line, sigma m. This is the maximum value, this is the minimum value, and this is the variable value, or the variable stress is above mean. The next one, again, for dynamic loading, we have these four different cases. With diagram, I'm trying to explain in brief manner. Completely reverse stress, extreme values of stresses are of equal magnitude and opposite in nature. Repeated stress, so the repeated stresses are there. Again the same thing, completely reversed means once it is say tensile, in another half the rotation or half the value, it will be in compression. Repeated means cyclic nature. Fluctuating means minimum value and maximum value. So repeated means from 0 to certain maximum. Fluctuating stresses means minimum value and maximum value of stress is of same nature. And alternating, so stress change in its nature and magnitude of extreme value of tensile and compressive stress is not the same. Alternating. So we may quote the example again of your bike or car's suspension system, wherein if you are driving on a cement road, newly constructed cement road, you'll have a smooth ride. If you go on the, say, some striated roads, in that case you will feel the alternating stress, where nature and magnitude both the changes. So this is a brief comparison of these four types of stresses in dynamic condition or in dynamic loading. The next one, most important part, design of components subjected to dynamic load requires. Please mind this particular paragraph very well for dynamic analysis. This particular aspect is very important as far as endurance is variable stress, endurance, fatigue, and finite infinite life is concerned. Because when we go for the dynamic loading design, in that case we have to consider all these factors. Now the next one is, these are the brief, in brief I am giving you the definition of fatigue strength and endurance limit, because this will be moreover repeated many a times now as far as our numericals are or the questions are concerned. It may be defined as the maximum stress that the material can withstand for specified number of stress reversals or cycles. Now say for example this is a shaft. If I am applying a point load at this shaft, and if this shaft is rotating, Please mind, if this shaft is rotating, so number of cycles, how many? 10 to the power 6, this is not 106, 10 to the power 6 to 10 to the power 7 cycles in millions or 10 times of millions now. The material can survive infinite number of stress reversals if the induced stress is below this level. If the induced level is below this level, which level it is there? 10 to the power 6 or 10 to the power 7 cycles. And if the material gets passed with this test, we say that, okay, yes, our agency is right, okay, tested, okay there. Again, the same thing, endurance. It is the maximum capacity of a material. Yes, it is the maximum capacity of a material to withstand amplitude of completely reverse stress that the standard specimen can sustain. Here the specimen word is very important. Can sustain for an unlimited number of cycles without fatigue failure. If failure takes place before 10 to the power 3 or 1000 stress cycle, it is called low cycle fatigue. Otherwise, if it is 10 to the power 4 and onwards, it is called high cycle fatigue. But my dear friend, mind very well, in the absence of experimental fatigue data, which we generally do not have as far as dynamic loadings are concerned, we may use endurance limit for ductile, because steel is ductile, cast iron is brittle. So we may use directly endurance limit as 0.5 times of ultimate strength of ductile material. Please mind well, and 40%, that is 0.4 times of brittle material of SUT. So this is very, 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 very important aspect. The next and the most important topic is ascent curve. Why do we draw, or why do we study ascent curve? Because ascent curve tells us the behavior of metal and non-metal both, because we are doing this for metal and non-metal both. But purposefully, this ascent curve is very, very, very important for our metals, testing of metals, because fatigue properties will be tested by this particular specimen. We have to prepare this mirror polished specimen, and we will test this mirror polished specimen in a bending and reversed bending. Moreover, not reverse bending, simply not reverse bending, in torque rotation as well as reverse bending both. So we will apply extreme condition to this particular specimen, and if this specimen survives with those particular intense condition, then we say that the material is safe for the fatigue loading, generally used in aerospace application, and non-metal axial fatigue testing is preferred. There is no specified transition from finite to infinite. Now this particular element I'll explain here only. So basically this is the SN curve for metals, and this is SN curve fatigue limit for non-metals. Over here the curve, because the moment we apply number of cycles, the stress suddenly shoots up, and then gradually, as the time passes, as the number of revolution passes, it goes to finite life. Wherein we say that high cycle fatigue is there. Below 10 to the up to 10 to the power 3, low cycle fatigue. It is high cycle fatigue because rotations or the number of cycles are changing, increasing. And there is a knee. You just look at or concentrate on this particular arrow. There is a knee. Now, after this particular finite life, 10 to the power 6 or 10 to the power 7, depending upon the material, so we say that the material will acquire infinite life. Even though you are increasing number of cycles, sir, the stress will not change or increase. This is the ascent curve for metals. Now, this is the ascent curve for non-metals, because previously this line was kept for non-metals. So I'm explaining here. Why don't we get this knee here also, in this case also? Why? because this is metal and this is non-metal. Sir, we don't have sufficient strength that gets transferred from finite life to infinite life in non-metals. That's why there is no knee in the curve also. I think you are getting the things, because these two things are comparable. That's why I have kept it on the same slide, because you have to compare these things now. So this is all about SN curve. The next topic is theories of failure. It may happen today, because the theoretical part was very much covered today only. Now from next lecture onwards, we will be directly going for the numericals and the equations. So we won't be getting enough say time for covering up all these theory aspects. So this is the last topic, that is theories of failure. In uniaxial tension test, the failure mechanism is simple. As elongations are largest in axial direction, we all know that. In uniaxial means what? Sir, in uniaxial means along this direction. The load is applied in only one single axial direction. So the strains can be measured and stresses inferred up to failure. It may fail. If it fails in elongation, it is called tensile failure. If in compression, it is called compressive failure. In shear, it is called shear failure. But that is deterministic nature of failure. The failure conclusion becomes challenging when the loading is biaxial or triaxial. Now please mind this word when I say biaxial or triaxial. When I say biaxial or triaxial, it means that the loading will be done along this direction as well as along this direction also. So along the two planes or along the three planes also, 1, 2 and say 3. So in this case, the chaos may happen or created how to calculate the stresses, because the system is not uniaxial now. It is either biaxial or triaxial. So theories of failure have put forward, or hypothesis has been formulated and tested for different practices, and these practices are known as theories of failure and are used to analyze the failure of material under biaxial condition. I'm again repeating, these theories of failure are used and designed for biaxial or triaxial failures. Most widely used in biaxial failures, and these are the generally accepted theories of failure. Maximum principle or normal stress theory, also known as Rankine's theory. Maximum shear stress theory, also known as Guest or Tresca theory. Maximum principle or normal strain theory, known as St. Venant's theory. Maximum strain energy theory, also known as Hayes theory. And the last one is maximum distortion energy theory, also known as Henke and von Mises theory. There are certain other theories also, but these are the most predominant and generally used theories of failure in the design of mechanical components. Now we will go one by one for these theories, and these are very, very simple theories. But we have to understand the basic concept. Why do we study these types of theories? Maximum principle oblique normal stress theory. In this theory, the failure or yielding occurs at a point in a member. Now please, again I'm repeating, in a member, when the maximum principle or normal stress system reaches limiting strength of material in a simple tension test. Now when we say simple tension test, the system would be biaxial only. So I'm applying tensile test in this direction as well as in this direction also. So in this case, the system would be biaxial only. So in that case, the material would be written as sigma T1 is equals to, or simply sigma T is equals to sigma YT upon factor of safety, or sigma UT upon factor of safety, depending upon the nature of or type of material. Where sigma YT is yield point stress and sigma u is ultimate strength. Theory is based on failure. My dear mind well, this is the basic theory which we are using in static loading also. In static loading also, this is the basic theory of design. So theory is based on failure in tension. Simple theory, but we are using this for biaxial onwards now. So based on failure in tension or compression and ignores the possibility of failure due to shearing stress. This theory considers only tensile or compressive and no shear stress is concerned. That's why this theory is not generally used for ductile materials. Yes, it is not used for ductile materials, my dear friends. Keep this thing in mind. Maximum shear stress theory, Guest or Tresca's theory. Very important for ductile material. According to this theory, the maximum shear stress in a biaxial stress system reaches a value equal to shear stress at yield point equal to shear stress at yield point. In simple tension test, mathematically how we can write this? Tau max is equals to tau yt. So please mind this well. Maximum shear stress in a biaxial stress system. Tau max is maximum shear stress in biaxial and shear stress at yield point. So this is again very important as far as ductile metals are concerned. Again, there is a relation. Shear stress is nothing but the half of yield stress in tension. This is the basic secondary equation used if we know yield stress and we want to calculate maximum shear stress of a component. This theory is mostly used in the designing members of ductile material. Now, the next, coming over to this theory, again very important theory for both ductile and brittle. According to this theory, the failure or yielding occurs at a point in a member when the maximum principal or normal strain in a biaxial. So this is strain theory. Yeah, strain. What is strain? Change in dimensions upon original dimension. So strain at yield point as determined from simple tensile test, the maximum principal or normal strain in a biaxial stress system may be written as. So these relations are very important. Strain at yield point, maximum strain at yield point is equals to sigma T1 upon E minus sigma T2 upon M into E, where sigma T1 and T2 are the principal stresses in biaxial stress system. Generally, sigma T is considered along X direction and sigma T2 is considered along Y direction. So, according to this theory, maximum strain at yield point may be written as equal to sigma yt upon E into factor of safety. This is the final equation where we can say that this equation would be used for both ductile and brittle, but not for any specific material. The next one, since I have written here, not for specific, this is not used in general because it only gives reliable results in particular cases. May be used for both the things, but not in general practice. Maximum principal and maximum shear stress theories are in working or use. The next is maximum strain energy theory or Hayes theory. According to this theory, the failure or yielding occurs at a point in a member when the strain energy per unit volume in a biaxial stress system reaches the limiting strain energy. That is strain energy at the yield point per unit volume as determined for simple tension test. The next, this is the equation generally we derive for biaxial stress system, and the limiting strain condition is written along two directions, that is U1 and U2. There is along x-axis and along y-axis. Again, the suffixes sigma T1 and T2 resembles the same along x and y with reference to the coordinate system. The last theory is maximum distortion energy theory, Henke and von Mises. This theory is mostly used for ductile material. in place of maximum strain energy theory. Again, the same thing. It is being replaced. The maximum strain energy theory is replaced by this theory, maximum distortion energy theory, where Henke von Misses are generally used in computer-aided design and analysis also. Von Mises stresses are very much, you must be very much familiar with the von Mises stresses in computer-aided analysis. So according to this theory, the failure or yielding occurs at a point in a member when the distortion strain energy, also known as shear strain energy. Now, what is strain energy? The energy stored in the body. The energy stored in the body. When when an elastic body is subjected to some external force. So strain energy, which is stored in the body per unit of volume. Which energy? Shear strain energy in a biaxial stress system. Now please consider the example wherein we can say that this body is subjected to, because shear is there now. Yes. So in this case, shear strain, when I say shear strain, it means that the amount or the nature of loading, one may be tensile, the another may be compressive. So in simple tension test is there because in one direction if it is tensile, in another direction it would be compressive. So maximum distortion energy theory, the yielding would be expressed as sigma T1 square plus sigma T2 square minus sigma T1 T2. Sir, this is very, very important relation and generally asked in the examination as far as questions are concerned. So we'll be using this in the next lecture. The theory is mostly used for ductile material. And I think we should end up today because question and answer, it will be dealt in next lecture. So thank you so much. Thank you so much. And we will continue this in the next lecture. Madam?